performance views.
Thank you. Hi everyone, I'm Vikas. I'm a postdoc at the University of Vienna. This joint work with Adrian Constantin in Vienna. Miles was a postdoc at Vienna as well, but recently, just last week actually, he started as a lecturer at the University of Bath and also with Darren. So today I'll be, well, just one note is that if you see anywhere a combination of these letters, it basically means the 4 authors listed here. Today I'll be talking about some new exact solutions to the steady 2D Euler equation, which combines Stuart vortices and point vortices, and which we are calling hybrid equilibria, and also some connections to various areas of mathematical physics, polynomials, etc., that have been being discussed during this week here. Okay, so we start with the planar Euler equation. So if uv is the velocity field components and you have a flow in an xy plane, p is the pressure, rho is the density, then you have the 2D Euler equations here. And the vorticity is basically the curl of the velocity field. In 2 dimensions it has only one component in terms of u and v, and by eliminating the pressure from these 2 equations here, 1a and 1b, you can get an equation for the vorticity. This is the vorticity equation, and basically the physical interpretation is that if you have some fluid particle which has at time t equal to 0 some vorticity, then it is basically advected with the particle. Okay. So we can formulate this, the vorticity equation in terms of a stream function. So basically you have the conservation of mass, which basically is the divergence free condition on the velocity field, which means you can define a stream function psi, and you can write the vorticity in terms of the stream function, and therefore you can write the vorticity equation in terms of the stream function. So at this point, just to look at 2 pictures of vortices, I suppose. So basically this picture on the left is the north pole of Saturn, and you can see a sort of a hexagonal pattern here. I'm not sure if it's visible, but basically this polar vortex is a persistent vortex. It doesn't decay, it's permanent, and it has this very interesting hexagonal pattern, and the question is whether you can explain, there are of course various explanations, but the question is whether you can model it using some simple solutions, and we tried doing that, and you can, I hope, see some sort of hexagon here, and so the point here is that it's so motivated by some such physical applications, we will be discussing some solutions of the Euler equation. Okay, so here's the vorticity equation. And let's first look at 2 types of solutions, point vortex solutions and Stuart vortices. So what are point vortices? They are the solutions of the unsteady vorticity equation with these Dirac delta vorticity form, and they are basically located at these positions zj. Z is the complex plane, and the gammas are their circulations or strengths, and there are m number of them. And if the vorticity equation is steady, then you can write the solutions in this form. Basically the Laplacian is some function of the stream function. Clearly 8 satisfies 6, and the choice of f determines the type of vortex. So if you choose f to be the exponential function, then you end up with the Liouville equation, and the solutions of this are called as Stuart vortices. Were found by Stuart in the fluid dynamics literature. So those are Stuart vortices, and that's point vortices. So let's take a closer look at each in turn now. So the point vortices, being solutions of the unsteady vorticity equation, have a dynamics. So basically the stream function is logarithmic, obviously, and there's a complex potential that you can define, and the stream function is the imaginary part of the complex potential. So basically this is, as we all know, potential flow, and the motion of the point vortices is governed by these Helmholtz laws, prime on this sum basically means that you don't sum over j equal to k, that is you leave out the infinite singular part. These were basically described by Helmholtz more than 160 years ago, so this is a very old subject in many ways. We are interested in point vortex equilibria, which are basically so a relative equilibrium configuration is where the vortices are stationary with respect to each other, but they can be translating or rotating as a whole. But the most, our attention in this talk will be focused on stationary equilibrium when they're all completely stationary. So there's none of the vortices is moving, therefore you have this relation to be satisfied by each vortex. And you can also, we have seen these sort of what do you call it? So extremum problems before during this week. You can also obtain these equilibrium conditions, 13 for example, by requiring that the Hamiltonian energy of the point vortex system is minimized subject to the constraints, which are basically the conserved quantities of the system. And but if you have completely stationary equilibrium and steady flow, it's basically the same as a 2D Coulomb gas. So it's the same patterns. Okay, so now there's quite a bit of literature on vortex equilibria or vortex dynamics in general and various other areas of mathematics. So point vortex dynamics, for example, is described as a classical mathematics playground because of this, and you can actually find on the subject of vortices and polynomials 2 different papers by 2 different authors with the same title, which is probably a bit rare, by RF and Professor Clarkson here. So I'll just give one example and then move on to the cases that we will focus on. So if you have m vortices of equal strength, gamma, so they're all 1, on a real line, then they have to be at the roots of the mth Hermite polynomial. So in that case, they're not all stationary, but they're all rotating at the same angular speed omega, which you can set equal to 1. As we know, the roots of the Hermite polynomials are all real, and they are on the real line. And so basically, if I just go back, so equation 12 here basically sort of reduces to Stieltjes relations. Because all the z's here are real, so therefore the complex conjugate on the right hand side is not it doesn't matter. So but we will consider these 2 polynomial systems today as it is my major focus. And basically, if you have vortices of strength plus minus 1, now you have mixed strength but the same value, the same magnitude. And they are at the roots of successive Adler-Moser polynomials, which were described by Adler and Moser in connection with the rational solutions of the KdV equation. And they had a construction where using iterated Darboux transformations. And the second set of polynomials, is actually 2, are more recent, described by Lutsenko, so we call them Lutsenko polynomials. These are basically vortices of strength 2 minus 1 and 1 minus 2, and they are at the roots of Lutsenko polynomials. Now, neither of these papers actually explicitly concern themselves with vortices. Lutsenko, for example, had various other considerations, and also some he talked a bit about the configuration of charges. But it's the same thing that's applicable for vortices. I'll describe them more in a bit. So let's now look at Stuart vortices. So they are solutions of the Liouville equation, and the Liouville equation has a explicit solution in terms of this function h of z, complex valued function. So basically, h is arbitrary in the sense that you can, whatever h you choose, you will still be solving the Liouville equation, except that there are some constraints that you impose if you want particular types of solutions. So let's say you want smooth solutions of the Liouville equation, then obviously you cannot have zeros in h prime, because otherwise you will have logarithmic singularities. Another observation to make here is that simple poles in h, not h prime, h, are okay because you have a fourth power here and a second power in h prime there, so the simple poles in h cancel out, and therefore they are okay. And just a quick note that this is on the plane, but you can also do it on a sphere, and more recently Takashi has worked it out on a torus, and you have to modify it to work on those geometries, but it will work. But that's not something that we'll be concerned about today. Okay, so let's look at some smooth Stuart vortices. So basically Stuart's original solution corresponded to this choice, basically a tan function. So h prime doesn't have any zeros, it's everywhere smooth, and this is the stream function. Now we want to focus on the role of this constant that appears very simple at first, that appears in front of this h and h prime. So if you look at what happens inside, you can do a little, you can substitute and do a little algebra, and you end up with this form for the argument of the logarithm, with 1 over a here and a here. And this is something that will be recurring throughout this talk. We will be interested in looking at these limits, where a goes to 0 or infinity. In both limits, you end up with a point vortex rho. So just to emphasize that, the Stuart solution here, the stream function, is not an irrotational solution. The vorticity is nowhere 0. It's the exponential function. But if you take this limit, you end up with an irrotational flow where the vorticity is just point vortices. And you can also take other limits, but they're interesting from a fluid dynamics point of view, but we don't bother about that now. Okay, so we saw smooth Stuart vortices. We also have point vortices. What we want to do is to combine them, and we call them hybrid equilibria. But why are we interested in doing this? Well, so basically Adrian and Robin Johnson had this paper a few years ago where they are looking at or modeling these large scale flows in the oceans of the earth called gyres. Now these are sort of permanent features of the earth, and they don't, it's not seasonal. And if you are, like, for example, and they are, and they are very large scale, so there you can see the 2 in the Pacific Ocean, the 2 in the Atlantic Ocean, 1 in the Indian Ocean, and they are basically on the order of several thousand kilometers, their radius. And you can also have many smaller ones. There are some near Antarctica, in the Arctic Ocean, and so on, which have size of hundreds of kilometers. And what they did in their paper is basically they used this equation, which we just saw, but we saw with f exponential, but they considered f to be either 0 or a constant or linear, linearly dependent on psi and so on, and so obtained some exact solutions and used them to describe these gyre flows. Now and then later we published some work recently where we have looked at actually well, just to emphasize that this is now on a sphere, but if you can do it on a plane, it's not very hard to do it on a sphere, because as I said that now we know how to do it on these geometries. So anyway, so recently we published a paper where we took f to be exponential function, that is Stuart vortices. And so Adrian's question was, is there any way to combine these Stuart vortices with point vortices? Initially we were thinking, I don't know, maybe there is some small vortex that's doing something inside the gyre or something like that. But eventually, but that's the sort of motivation for why we are considering these hybrid type solutions. Okay, so these are the smooth solutions. If you take the Liouville equation, what we want to do is to obtain solutions for the modified Liouville equation, where we have added a bunch of point vortices. But the point vortices, of course, are unsteady. They can move about, and so we have to, if we want steady solutions, we have to impose the condition that they are stationary. So basically for z not equal to zk, zk being the location of the vortices, you have the same old Stuart solution being valid, or Liouville solution being valid, but at these points you have to ensure that the velocity you find from this solution after subtracting off the singularity due to the point vortex is 0. It's so that the point vortex is stationary. So that's the kind of definition of what we are trying to do. Okay, so I'll first look at one rather simple example, you might say, and this was actually considered by Crowdy many years ago. So I should maybe clarify here that now Stuart originally wanted smooth solutions, but if you try to extend it to a sphere, it's not possible to get everywhere smooth solutions on a sphere. So you have to include some singularities, and basically this led to Crowdy to publish this paper where you also look at what happens if you add some singularities in the plane. And if you have one singularity in the plane, it's not very hard to see that it has to be stationary, and so therefore everything is fine. But if you have more than one, then it becomes very, I mean, you need to do a lot more to actually figure out how it works. So if you have just one point vortex, which corresponds to taking h prime to be just z, because then you can see that at z equal to 0 you have a point vortex, a logarithmic stream function. And then you have this h, and then you put it into the Liouville solution, and again the one thing we are interested in is to take the limits of what happens as this constant a takes these limiting values 0 and infinity. So basically you do a little algebra and you end up with this form, which is very similar to the form we had in the Stuart case with a 1 over a and a. And if you take the limits a tends to 0 or infinity, one of these remains, the others goes away, and you basically get the corresponding point vortex. So if, for example, a is 0, then this goes away. Now, of course, you still have, if a is 0, you have log 1 over a. So you have to sort of subtract off an infinite constant, but that's fine. Constants added to stream function don't matter. And then you have a single point vortex at the origin. On the other hand, if you have a tends to infinity, this is 0, and again after subtracting off this infinite constant, you have not 1 but 3 point vortices. And that's this, the single point vortex is this. So this is sort of the picture that you get from this example. Now when a is neither 0 nor infinity, you will have a sort of rotational flow with point vortices, with a single point vortex rather, and everywhere else it's a smooth flow, smooth vorticity. Okay, so let's see what this limiting thing looks like in just a general case. So what I mean by general case, so let's see, so this is the solution. I'm going to just rewrite it slightly in this form. I've just dropped the explicit dependence on z, but it should be clear. And then I'm going to look at functions that look like this. So basically h prime is a times h tilde prime, where a is some constant. And then if you put that in here, you get this form. You get a log of 1 over a times something plus a times something. And once again you take these limits a, 0 and infinity, and you get point vortices if you consider h tilde prime to be some rational function, because then clearly you'll have just zeros and poles and they are all point vortices. But are they all stationary? Because then you can say, okay, so this is like a steady solution. So to answer that question, we proceed like this. Suppose you have h prime is h tilde prime, but h tilde prime is defined like this, as in 28. Now we have actually seen this type of function many times during this week. Sometimes it might have been varying a modulus, but taking a modulus there is just considering the stream function instead of this complex potential. So if you consider this function and you restrict gamma j to be integers or half integers, so that h prime is rational, then for positive gamma j you have zeros at zj, and negative ones you will have some sort of poles. And then we are interested in the question, it will be clear shortly why we are interested in this question, but we are interested in the question, what is the condition to be satisfied for so that if H prime is rational, then H is also rational. Now this question is quite old. It was actually, so maybe I can we haven't formulated it this way, but I can just write it here. Suppose H prime, I write it as, I choose gamma such that H prime is the square of a rational function with numerator p and denominator q. So this so then if H prime is rational, so H is the integral of this, and is this rational? That is, does it have logarithms? So this question was asked by Buchnall and Chondi a long time ago, and they showed that this is actually rational if P and Q satisfy this differential equation, which is called the bilinear differential equation. Okay, so let's just keep that aside. And but we won't be actually thinking along those lines, but instead what we do is you use a local Frobenius analysis for this H prime near each pole, and you can then see that, I mean, if you expand it, basically gamma j cannot be minus half, minus 1, minus 3 by 2, minus 2, and so on, because then you will have poles in H prime at those locations. Now, I mean, at first sight it might be a bit disappointing, because, I mean, then you are left with nothing if none of those values are allowed, but you quickly realize that these are sufficient conditions, but they are not necessary, because you also have the coefficients in the Frobenius series, and these coefficients can be 0. And for example, so gamma j of course cannot be minus half, because then you clearly have a simple pole, and so that's never allowed. But you can look at the next one. What about gamma j is minus 1? So it turns out that gamma j is minus 1 is always allowed. It doesn't matter, it's always allowed. Why? Because the Frobenius coefficient of that is basically the point vortex velocity field, and if they are all stationary, then that is 0. So that means that term will never show up. Now gamma j is minus 1 basically corresponds to a form that looks like this, and what Buchnall and Chondi showed is that if you have this type of rational function, and if H is also a rational function, so basically these P and Q are called the Buchnall-Chondi polynomials, or also they were constructed in a different way later. This is basically also the Adler-Moser polynomials. So if you like, this is sort of a physical proof, you could say, for why the Adler-Moser polynomials, I mean the Darboux construction always gives you polynomials. Okay, so what does all of this have to do with our stationary solutions? Well, so here's a further thing to consider. We make the following claim. Suppose H prime is this guy, then H hat prime defined like this is also an equilibrium. So if H prime is an equilibrium, that is, if it is formed from Zj such that all these Zj's are all stationary, then you form this H hat prime where alpha is some real number, then that is also an equilibrium. It doesn't matter what the Zj's are, what the circulations are, and so on. And well, I mean, I'm not going to go into how to prove this, but you can prove it. But I want to compare it with a previous equation we had. So let me just write that down here. So I write the second one. So H hat prime is A hat H prime over H squared power alpha. And let's compare it with 27, which is this, which was the general. So now I was just discussing about point vortices, and I just want to emphasize this. But now 27 is basically a solution of the Liouville equation, and this this is something that that is important in the sense that both of these questions appear to be very intimately connected. The answer to one also leads to the answer to the other. So let's look at the argument of the log in this Liouville solution now. And if you look at this, for example, the second term here, it looks kind of like this. I mean, it's 1 over, is okay, but it looks like this, h prime over h square, which is actually how we found this transformation from this. And what's the role of this alpha? There's no alpha there, but if you think about it physically, if you look at this equality here, so what's log h prime? Log h prime is basically just the complex potential, and physically it doesn't matter. You can add any number of constants to the complex potential. It will not change anything, and that's what is the role of a hat. It's basically just a constant in the stream function. And alpha, if you have any point vortex equilibrium and you scale all of the circulations with the same number, it doesn't matter, it stays in equilibrium. And that's what alpha is doing, because if you take a log, this alpha will appear in front of the log. It's basically the circulation. So therefore, well, that's not a proof, but that's kind of the argument for why this transformation works and why it would produce another point vortex equilibrium. Okay, and then we can iterate this transformation. So you have you start with some n equal to 0, you have an h naught prime, and then you have h1, and then you have an h1 prime, and so on. You keep going. Okay, so let's compare it with some known hierarchies. So what we actually find is that you can take this simple seed function. H naught prime is basically just a point vortex at the origin with strength gamma naught. And this single seed function with this same transformation can reproduce all of these hierarchies. So you take gamma naught is 1 and you pick alpha n to be minus 1 for all n, and you get the Adler-Moser polynomials. I'll come to these others later, but if you pick gamma naught is 2 and you pick alpha n to be minus half n even, that means you start with minus half. So the first step, alpha n is minus half, then it's minus 2, then minus half, minus 2, and so on. Then you end up with the, well, this is basically, I mean, so Lutsenko has two different hierarchies of polynomials. For the present, we are going to differentiate between them by saying I greater than or equal to 0, I less than or equal to 0. So you get one of the Lutsenko hierarchies. And you pick gamma naught is half, and you now, instead of starting with minus half, you start with minus 2, and then you do minus 2 minus half minus 2 minus half. In this iterated transformation, you get the other Lutsenko hierarchy. So one way to look at this transformation is sort of as a generalized Darboux transformation, because if you pick alpha n is minus 1 and you set hn prime is some phi n of z square, then phi n is basically the rational function you get from the Darboux iteration. But it also it's a generalization because it can also reproduce these other hierarchies. And there are other values that you can take. So gamma naught is half and alpha n is minus 1, ends up in a finite length hierarchy. It's a terminating one. I'll show the examples for all of these shortly. But if you do others, you end up either with a special cases of these, or you end up with some logarithms or not point vortices and so on. I mean, it's not random. You can kind of, there's a pattern. Okay, so let me show you the some examples. So here you have Adler-Moser polynomials. What happens is that if you choose, because at every step you have integration constants, if you choose them to be all real, they'll be symmetric with respect to the real line. And if you choose them to be complex, and that's what's shown here. And so in each row, it's basically the steps in the hierarchy. And in the second row, you have asymmetric case. And yeah, maybe, I mean, there's interesting stuff happening here, but I think I'll just skip those. And then you have the Lutsenko hierarchies. Well, I should just explain. So the black dots here correspond to vortices with negative strength. The blue diamonds are positive strength, and the size reflects their value, their strength. and you can get various types of equilibrium patterns in this way. And you can also have the terminating ones. If you start with a single one with half, it terminates in one step. If you start with 3 by 2 in 2 steps, if you start with 5 by 2 in 3 steps, and so on. So you can get these finite length hierarchies. Again, these are symmetric because of the way we have chosen the constants. You can choose them to be asymmetric. It doesn't have to be hierarchies. You can start with, there are non-hierarchical ones, but it always works for one step. The transformation always works for one step. So you can start with something like this, and you produce an equilibrium that looks like this in panel 2, and you can do various things with this to get like all equilibria that look like this. Now, if you see this, it may be hard to believe that this is actually an equilibrium, and it was difficult for us to believe, but you actually have the explicitly, you know what the locations are. You can feed it into the Helmholtz law and check that it is actually an equilibrium in many of these cases. I mean, in fact, any of these cases. Okay, so so this was about point vortices. Now so here's a schematic. So you start with some seed, and these black squares are basically various point vortex equilibria that you produce through this general transformation path, which I've called discrete. Now, what does Liouville have to do with any of this? Well, it turns out, and this is I think quite amazing, is that once you have proved that this transformation basically produces point vortex equilibria, that's sufficient to show that the hybrid equilibria also works. That proof is already there in it. So so in a sense, we have already proved that the Liouville solution also works, just with these, but with these irrotational solutions. And these what this Liouville path is doing, what I've said continuous, is that the value of these parameters, when it is 0 or infinity, you are at these point vortex equilibria, but when it is finite, you are somewhere in between here on this red line. And for each of the point vortex equilibria I showed, you can be in somewhere in between that red line, and you can produce these equilibrium solutions. Now they are not irrotational. Everywhere there is Stuart vorticity. You can do this for all these cases, and we can look at figures until the night, I'm afraid. So okay, so just to summarize then, so basically we found that there is a general transformation linking different point vortex equilibria, which automatically ensures that you, because of the structure of the Liouville equation, that you also have solutions to the Liouville equation, and then you can do this, you can iterate this, and you can produce these iterated hybrid equilibria, or non-iterated ones, or terminating ones, whichever ones type of ones you like. And so these are some of our published and upcoming papers. Thank you. We haven't tried it, but we think that it will produce doubly periodic equilibria. Yeah. I mean, Stuart's original choice was singly periodic after all. So. Yeah. So, I mean, it would work.
Starting with the plus inside equals e to the side, generating that. There's one other function that might be interesting, perhaps you've looked at it, the plus inside the sine side, the Sept-type.
Yeah.
There's a lot of special solutions, and that's some kind of A equations.
I see.
Hang around.
No, we haven't, although actually the Stuart people in the books have taken the Stuart model and added, changed the x for a cinch.
Yeah.
Then looking at his Mali and Maslow vortices.
Yeah.
But this, we certainly haven't looked at whether these hierarchies. What's the interesting new, just to emphasize, the interesting new thing about this is that, as you said in that final schematic, you have these isolated point vortex equilibria, these hierarchies. They're pure point vortex equilibria, but they're connected by these smooth Liouville interpolates that are all equilibria.
Yeah. So
there's a fascinating connection I haven't seen for vorticity.
Yeah. So if you can just add a sentence. So basically, these discrete transformations are also all dependent. At each stage, you get one complex valued parameter. So at the nth stage, you have a solution with n complex valued parameters. And the same thing is true for these continuous solutions. They're also at each stage, you get a complex valued parameter. So in a sense, we are generating steady solutions of the Euler equation, which periodically goes over to irrotational solutions, and in between them it continuously sort of extrapolates and interpolates with rotational solutions.
Okay, we better stop there. Thank you once again, Vikas.
And we'll start in 20 minutes.